Suppose that we are investigating the flow over a bluff body, an external flow, and here is the stagnation point of this flow. And I'm asking you about the pressure, the coefficient of pressure at the stagnation point here. This part is selected from the viscous fluid flow written by F.M. White, and this is the section related to the stagnation point flow, as you see, section 381. Viscous flow over near stagnation point. Here, this is the schematic geometry of the problem. This is the stagnation point shown by 0. And the other name is Hyman's flow. He was one of Prandtl's first students. This is a close snapshot of the stagnation point near the nose of the body. So if you focus on the nose of the bluff body, the curvature of the body will be omitted, and something similar to the previous figure appears. So the question I'm asking about the pressure coefficient of this flow at the stagnation point. I just want to omit the mathematical procedure of the solution, and I'm referring to equation 3157, and this is the pressure distribution in different points in the flow field. As you see, this is the stagnation point pressure, 0 and 0. This is the stagnation point, and this is the pressure at another point inside the flow domain. When you're going to compute the pressure coefficient, so you have to compute the difference between the stagnation points, because you're going to compute coefficient of pressure at the stagnation and the pressure of the incoming fluid or the upstream flow. So in this relation, replace eta by infinity. So and also divide both sides of the equation by half of the product of the density and the magnitude of the upstream velocity, which is u squared plus v squared. So this is the dynamic pressure. This term here is called the dynamic pressure. So when eta is infinity, from the boundary conditions in this figure, as you see, when eta goes to infinity, the value of f prime becomes unity. So in this relation, f prime should be here. F prime in this term, in the last term, f prime should be unity, and also divide both sides by the dynamic pressure. So the left hand side will be the coefficient of pressure at the stagnation point, and the right hand side of the equation will be unity plus something. This term is a positive term because B, viscosity, and also the dynamic pressure are all positive quantities. So you observe that the coefficient of pressure at the stagnation point is unity plus a non-zero quantity. So the coefficient of pressure at the stagnation point is always greater than unity. But as you see here, we have the viscosity of the fluid. So when the viscosity is negligible, or the Prandtl's assumptions or the boundary layer assumptions are valid, so you can ignore this term and approximately suppose that the coefficient of pressure at the stagnation point equals unity. But this term never vanishes, and always the pressure coefficient is greater than unity. And the other situation at which the pressure coefficient is greater than 1 is for the compressible flows. Here, suppose that the incoming flow is compressible with Mach number greater than unity, or the supersonic flow. Here we may have a detached shock wave, and the presence of a shock wave inside a compressible flow leads to the reduction of the stagnation pressure in that flow. So the stagnation pressure of the incoming flow before the shock wave is greater than the stagnation point of the flow after the shock wave or behind the shock wave. So the pressure of this point, which is the stagnation point of the flow behind the shock wave, differs from the stagnation point of the incoming flow. This may lead to the non-unity value of the coefficient of pressure at the stagnation point.